3rd, 2016, and in 1 week we have our first regular exam. We have, of course, the mini exam back like 3 weeks ago or so now. What is the regular exam on? Well, mostly chapter 7 and the first 4 sections of chapter 8, as well as the last 2 sections of chapter 8. The only parts of chapter 8 we're not doing are sections 8.5 and 8.6 for this first regular exam. Those will be the main topics we do after the first regular exam. And of course, reviewing everything, making sure you can do all your integrals and you understand the meaning of integration and fundamental theorem of calculus. Things you were tested on for the mini exam as well could show up on this regular exam 1. Question?
Is there anything particular that we should study in mathematics for the exam? Because you said we would have to write some math.
Yeah, mathematical code, basic code involving manipulating the trigonometric plot.
Okay.
And I'll talk about that. Today we're going to do, well, I'm going to show you a realistic lifetime random variable for the lives of people. We're going to do one more new topic, and this will be the last new topic before regular exam 1 next week. Mass densities for what are called thin bars and thin disks with radial symmetry, and center of mass for the thin bars, I should probably add there. That'll be our last main new topic before the exam. Come back to polar coordinates, parametric curve, position, velocity vectors, arc length, and area swept out in lecture B. Actually, area swept out we haven't talked about yet either. That'll be something new. Wednesday, we're going to put it all together, try to review everything that we've done, summarize it, get it in our minds, what have we done so far. And Friday you have off, so you have a long weekend to prepare for the test next Monday. Okay? But I think Math Lab is maybe not open on Thursday or Sunday, so if you want to use Math Lab to get your questions answered for the test, you should start studying today and go to the Math Lab today, tomorrow, Wednesday. It should be open for those days. All right, what is this more realistic model? Well, I just made it up this morning, okay? So this is a model that I made up. I'm not claiming this is perfectly realistic by any means, okay? It just is more reasonable than the models we've considered so far. I made a piecewise function here. That's got 4 pieces to it. Where did I come up with these formulas? I was experimenting with it until I got a graph that seemed pretty good, okay? That's what I did. What does the graph look like? It looks like this. This is my PDF for my more realistic model for lifetimes of people. Typically the oldest living, I think the oldest living person is around 118 right now. In fact, I think there's only one person officially left alive in the entire world who was born in the 1800s. Okay, I think I saw that in an article a few months ago. It's like one person, at least officially by official records, one person who's still alive who was born in like 1899 or something. So 120 seems to be the upper limit on ages. What's the nature of this PDF? Well, since the bulk of the area is between ages 25 to 120, most of the people, most of the newborn babies are going to die in that age range. I've got a little bump up right here because of infant mortality. Infants die at a higher rate than, say, 2-year-olds do, or 3 or 5 or 10 or 15-year-olds. So there's this little bump up because of the fact that more infants die than 2 or 3 or 4 or 5-year-olds, etc. Got to go low until you hit 25, then it starts going up for the PDF. I don't claim this is perfect, okay? It just seems more realistic to me than the models we've considered so far. The uniform, the straight line with a positive slope, and the exponential model. This seems more realistic. I can do the same things I've done with this before. I can graph it in such a way that, well, I shade appropriate areas. There I've shaded the area from 30 to 70. So whatever that area happens to be, and you can figure it out as the area of a trapezoid, that would be, for this newborn baby, the probability that that baby would die between the ages of 30 and 70. This does only apply to newborn babies, by the way. If somebody's already lived to age 80, for example, you would not calculate the area from 90 to 100 to figure out the chances that they will die between 90 and 100. This only applies to newborn babies. That's the idea. But that area, whatever that is, would be the chances that that baby will die sometime between the ages of 30 and 70, or in a more positive light, the chances that they will live to age 30 to 70. Okay. I can use a built-in Mathematica function called probability distribution to sort of store this distribution in Mathematica. You don't need to understand what that means exactly. I can graph the CDF for this function. Remember, the CDF is the integral of the PDF. It's an antiderivative. And if it's a lifetime random variable that starts being non-zero at 0, the CDF is going to go through the origin for its graph and increase up toward 1. In fact, it will equal 1 once we get to 120. This takes a little while to compute because it's doing a lot of calculations. There it is, it goes to the origin, and when you get up to 120, the second coordinate at that point is 1. So that's the CDF in this case. It doesn't look all that remarkable, perhaps. How does it relate to the PDF? Well, the derivative of this is given by the PDF. The slope is pretty low here until you reach age 25, and it starts going up after that, because of the fact that the derivative is pretty low right there. I mean, I can't really see it, but the derivative is actually fairly high right here, relatively speaking. It goes up real fast for a small amount of time. Then it goes up very slowly. Then once you hit 25, it starts to go up faster and faster because the derivative keeps getting higher and higher. And because the value of that PDF is highest at age 80, that means the slope of this one is highest at age 80. That's the inflection point right about there. I can do simulations with this, well, and I can calculate a mean and a standard deviation. Mathematica says these things are 73.3 and 21.2. Actually, we haven't talked about standard deviations before. It's a measure of spread. The mean of this distribution is supposed to be 73.3 according to this command. Technically speaking, you should be able to verify that. You know the formula for the mean already. Let's have Mathematica do it for us, but you know what to do. You should know what to do. Do the integral over the entire domain, 0 to 120, of t times the PDF. T times f of t. You should know for the exam in 1 week that that's how you calculate the mean. So, if I enter this as is, it's probably going to give me a fraction. Yeah. But that fraction should be 73.281. Percent sign refers to the preceding output. / capital N will do a numerical approximation. This should be 73.281. And it is. So you know that this is how to calculate the mean. And this would be the mean age that a person according to this model would live. Okay? Seems a little low. These days, people tend to live more toward closer to 80 on average. Okay? So my model's not perfect, but you should know that. Would that be terrible to do by hand in this case? You'd have to do it piecewise. You'd have to take the formula, each piece of the formula, way up here, multiply it by t and integrate over each piece of the domain according to these things, and then add up all the results. It would take a while. If I had to do it by hand, how long would it take me? Probably take me 10 minutes. I can calculate pretty fast. So if you had to do it, it would not be an exam problem, okay? Because it would probably take you 25 or 30 minutes and you might make a mistake. Or it'd be easy to make a mistake. And we can still do simulations with this. Okay, so each dot is going to represent a baby who was born and lived to a certain age and then died. There's the data. Not showing all the data, it seemed to stall there. There we go. Notice the data is most dense where the density is highest. That's why it's called the density. Probability density function. Not very many data points over here, only one really that's below the age of 25. The area under the PDF between the ages of 40 and 100 looks like it's about 0.83. That would be your probability that the baby would die between those ages. 83% chance. And for these simulated data, 76 of the 100 people died between the ages of 40 and 100. If I enter it again, it's going to produce different data. I suppose I should look to see what A and B are. 40 and 100, pretty close? Yeah, pretty close. Let me enter it again. Once again, make A about 40 and B about 100. Close enough. Close enough. For these data, it was about 81 people in this simulation that died in those ages.
Oh, never mind. You're just seeing how many were in that range. That's
Right.
what they
That's what the last number means, yep. Okay? So you can do simulations with this even though it's not a standard kind of distribution. The uniform, a straight line, exponential, those are all kind of standard distributions. Okay? This is a made up thing. I just made this up this morning. It just seems somewhat reasonable. Okay? All right, so that was the first thing to do today. What's next on the docket here? Okay, masses, physics, mass densities, actual mass. Mass densities for thin bars and thin disks with radial symmetry and a center of mass for thin bars. Okay, let's focus on the thin bars first. Let's just make some white space here. Okay, imagine a really thin bar. A wire? Is that thin enough? Yeah, I guess so. Or maybe even thinner. Really super thin, like an atom thin or something. Okay, ideally it would be like an atom thin, though you can get away with pretty thin for this to be a somewhat realistic model. I will try to draw a little bit of thickness to it. So this is like a real thin bar of metal, kind of like a wire or something. Usually when you think about the density of something, you're thinking in terms of, right, of mass per unit volume, right? Thinking chemistry or physics. The mass of this thing is so many grams. What's its volume? Maybe its volume is, so many liters of volume, or so many cubic inches, or cubic centimeters, I should probably say. Mass might be kilograms or grams per cubic centimeter, right? Thinking about it as a three-dimensional object. When you've got a thin wire, thin bar of metal or something, you can make it more simplistic. You can consider a linear mass density. That is going to give you mass per unit length. Effectively treating it like a one-dimensional thing. Okay? For any x you slice this bar at, any kind of thickness you have to it, the density is basically constant. The book calls the linear mass density delta of x. Delta is just a function name here. I think sometimes you'll see books use the letter rho instead of delta for density. Our book uses a delta. I guess delta starts with D, like density starts with D. That's perhaps why. Let's say this is in grams per centimeter. Not cubic centimeter, per centimeter. That's not a typo there. Grams per centimeter. What's the goal? The goal is to find the mass of the rod. Shouldn't we just weigh it in the standard gravitational field and use that to figure out the mass? Well, yeah, that would be easier in real life, but we're trying to do things in calculus which sometimes means we're doing things theoretically. It's got benefits besides actually weighing things. Okay, to use this kind of approach has benefits that go beyond this kind of problem. So it's still worth learning this more theoretical approach. Get your knife out, you slice it at some value of x into an infinitesimally tiny piece. It's got infinitesimal length. What should I call that infinitesimal length? What do you think I'd call it? dx, yeah. I draw that little tiny infinitesimal length to have an actual length on the board, but you need to, in your imagination, pretend it's so tiny it's essentially less than any positive number. Again, this is conceptually kind of fun and intuitive. Rigorously speaking, in the standard real number system, it's not rigorous. Okay? Idea of an infinitesimal. And again, the book approaches things from the Riemann sum perspective, which you should read and try to understand. I think I will probably emphasize that more after the test. Here before the test, I'm trying to emphasize this differential approach that scientists and engineers would take. Okay? But again, they do know that if they get an integral that's hard to do, that they do have to do summations to approximate it or else use technology. They do know that. Okay, they are aware of that. So at some value of x, according to some number line, by the way, you'd have to have a number line in the background. Measurement, you'd probably start the bar at spot 0. And it would make sense, since the density is in grams per centimeter, that the length along the number line would be in centimeters. The bar has a certain total length, call it capital L. So you got to have some point of reference. Otherwise, your formula doesn't really make sense. You got to have, x has got to be in centimeters starting at some point for the formula to make sense. So what's the total mass? We'll start by thinking about what the little mass of the little chunk would be. This little chunk you've sliced off. Why not call that dm? Infinitesimal little amount of mass. What is it, 1 atom or something? Is that how small it is? No. Pretend you don't even know about atoms or molecules. Okay. When you're using this kind of approach, you pretend you don't even know about it. I mean, Newton and Leibniz, they may have thought that atoms existed back then, but nobody had really good scientific proof of it, as far as I know. I mean, the Greeks thought of atoms. So people had these ideas about atoms, but they didn't know what they were, that's for sure. And they didn't have good scientific proof of their existence back in Newton and Leibniz's time. So they didn't think about atoms, they just thought about little chunks. How do you find the mass if you know the density? Well, in three-dimensional objects, you take the density, say in grams per cubic centimeter, and multiply times the volume in cubic centimeters. The cubic centimeters would cancel. Same kind of idea here, except it's a length instead of a volume. Take the density times the length. This would be in grams per centimeter, and this would be in centimeters, giving you a result in grams. You're pretending that's a multiplication. Ultimately, you put that next to the integral sign, and it's not really a multiplication. And this is where it all gets kind of confusing, because we're not being rigorous. But that's the way they think, okay? And then the total mass, just call it M, is found by adding up the little masses. There's our conceptual equation. Conceptual equation. If I ask you on the test to write down a conceptual equation, in this case representing the mass of the object, or maybe in some other problem representing the volume of an object, you should understand that that's what I mean. I suppose you could call this a conceptual equation too, but this is the kind of thing that I've been labeling a conceptual equation. It doesn't tell you what to do. It just says, here's the idea: to find the total mass, add up the little masses. To find the total volume, add up the little volumes. Pretend the integral means add. But how do you actually do it? Again, here maybe I put an equal sign in quotes. Maybe I shouldn't, I don't know. I mean, we want to get to a definite integral so we can actually do the calculations. The idea, the definite integral, replace dm by delta of x dx. X goes, in this case, from 0 to capital L. And that'll be a definite integral that you can actually do. So, as a real simple example, by the way, these integrals are usually pretty easy, right? A lot easier than arc length integrals typically are. You know, sort of maybe a silly kind of example. Let delta of x equal 2 plus 3x as x goes between 0 and 4. Okay? You might scratch your head and wonder when this would ever happen. When would you ever have a formula for a density? It is a little fishy that way. It's a little phony, you might say. I mean, yes, there are objects that vary in density, but usually you wouldn't have a formula for the density, but we're pretending that we do. So the total mass, then I'm going to find by integrating this function from 0 to 4. And I made it a pretty easy integral. You know, even if I made that quadratic or cubic, it still would be pretty easy. Make this over in your mind with me, so you're checking to make sure I don't make a mistake. 2 times 4 is 8. 4 squared is 16. Divided by 2 is 8. Times 3 is 24. It looks like 32. Don't forget your units. Grams. If this is in grams per centimeter, and the x is in centimeters. That's pretty nice, actually. A pretty easy integral to do. Could make it harder, but it's not too bad. And with most typical functions we encounter, it's going to be relatively easy to do. Definitely easier than arc length integrals typically. Okay? It's the more abstract idea that's more important. Learning how to think this way will help you in future physics, chemistry classes, even biology classes. Instead of a mass density, this could be a bacterial density in biology here. You could have bacteria on a thin wire, and the density here could be in millions of bacteria or billions of bacteria per centimeter. And then doing the integral would give you the total number of bacteria. Same concept. What about densities along a circular disk, a thin circular disk with radial symmetry? So imagine a thin disk, like a DVD or Blu-ray that we hardly do anymore right now. Everything's online. It's really thin, even thinner than that. Got it on its side. You're looking at it straight on. It's got a certain radius. Call the radius here capital R. And it's got radial symmetry to its density. What does that mean? That means for any given radius, little r, from the origin, that's less than or equal to capital R, along the circle of radius little r centered at the middle, the density is constant. But if you change the radius, it could be a different density. Delta of r depends only on r, not on like an xy coordinate system. In fact, it's best to think of this in terms of polar coordinates. That's what I'm getting at. You can put an ordinary coordinate system in here, if you like, but really what we're interested in is what's the density along some circle of radius little r centered at the origin. Call it delta of r, once again. This is not going to be a linear density. It's going to be what you might call an area density. It's going to be in, say, grams per square centimeter. Units of mass per unit of area. Because this is a thin disk. The radial symmetry is going to effectively make it a one-dimensional integral instead of a two-dimensional integral. If it didn't have radial symmetry, we'd have to use multivariable calculus. Integrate with respect to both x and y. But the radial symmetry makes it a simpler problem than that. We can do it here as well, too, still. But it is a little trickier to figure out what integral to do. You don't just integrate delta of r. Because you're not slicing it perpendicular to an axis here. You're getting some scissors out and cutting thin rings or thin washers or thin annuli of width dr, infinitesimal width. These are really, really thin. Try to draw with a little bit of thickness here. But in your imagination, you need to imagine that having infinitesimal thickness. Thickness dr. How would you find the mass of such a thin ring, other than putting it on a scale? Think theoretically here. You'd have to take its area density, which is going to be constant, essentially, because we're at a fixed r, essentially, and multiply times its area. The infinitesimal mass of this infinitesimally thin ring should be the density times the area. Call it dA. This would be in grams per square centimeter, and this would be in square centimeters. But that just begs the question, what is dA? It would be the area of this thin ring, which technically speaking would be the area of the outer circle minus the area of the inner circle. However, because this ring is so thin, we're going to do something simpler, ultimately. Imagine taking the thin ring and cutting it in one spot and then unrolling it. What would it look like? It would look like a really, really thin rectangle. Actually, it wouldn't be a rectangle exactly, but it would be so close to a rectangle you wouldn't be able to tell the difference. dA is the area of the really, really thin, tall rectangle of width dr that you get by not only taking this, cutting this ring out, but also clipping the ring on the spot and unrolling it so it looks straight, pretending you can do such a thing. This is malleable, okay. These are all thought experiments, right? Just imagining you can do this. Technically speaking, it's not a rectangle. Technically speaking, one side's a tiny bit longer than the other. The outer circle has a tiny bit bigger circumference than the inner one does. But if that ring is sufficiently thin, you wouldn't be able to tell the difference. It would look like a rectangle. What's the height of that rectangle? It's the circumference of, say, the inner circle. 2 pi r. So dA, the area of that really thin rectangle, should be the area of the rectangle's height times width. 2 pi r dr. Now substitute that back into here in place of the dA, and your dm is 2 pi r delta of r dr, and that's what you integrate to find the total mass. So the total mass now is the integral of the little masses, which ultimately means you do an integral of 2 pi r delta of r with respect to r as r goes from 0 to capital R, the radius of the entire disk. This quantity right here is in centimeters. This is in centimeters, making this in square centimeters. Then you multiply it by delta of r, you get something in grams. It's a capital R here, by the way, if you can't quite tell. Capital R. Now once again, for your typical run-of-the-mill functions for delta of r, like a polynomial or something, that integral's not too bad to do. I could do an example. Is it okay if I don't? It's not that hard to do. You compare that to arc length integrals, this is a piece of cake. For your ordinary kinds of functions like linears and quadratics and cubics and so forth. And the integral does start at 0 because the little r starts at 0. So that'll make it nice, typically. The lower limit of integration is 0. Okay. This is all stuff in the book. You're going to want to look at it. One more thing before we take our little break and get into lecture B. And that is center of mass. Not for thin disks, but for thin rods. So now we're going to go back to thin rods. Center of mass for thin rods. Once again, I'm not going to explain the formula today. Wednesdays are going to be our big explanation day, okay, as well as reviewing. We're going to explain a little bit more rigorously where these formulas come from. The book does explain it's based on the law of the lever. The fact that if you've got a seesaw and one person is twice as the mass the other, the person who's half the mass has to sit twice as far away to make it balance. That's where this formula actually comes from. So again, we have a thin rod along an x-axis from 0 to L. The center of mass is denoted by an x bar, which is actually the same symbol used for means of data sets. And in fact, centers of mass are very much related to means. The formula looks like this. You can write it 2 ways. You can just put the word mass on the bottom. And on the top, well, okay, I need a density function. Delta of x is the linear density in, say, grams per centimeter. This is going to be a fraction here. This is not a thin bar there. The mass is going to be on the bottom of the fraction. On the top is going to be something that looks a lot like the formula for the mean of a random variable. In fact, it is the same. Integrate x times the density. Except the density here is a mass density, it's not a probability density. But it's the same kind of idea. Integrate x times the density. For a probability density, that is a PDF instead of a mass density. And the mass for probability densities is 1, because the mass essentially is the area under the PDF, 1. So this does actually simplify to the mean of a random variable when you know the PDF. Another way to write this is to have an integral sign on the bottom as well. Integrate x times delta of x up top. Integrate delta of x itself on the bottom. By the way, when I wrote my original equation about 20 minutes ago for the mass of the thin rod, did I put limits of integration 0 and L? Anybody write that down? Did I? Okay, that's good. Same limits of integration. By the way, I mean, again, this is only if you start the one side of the rod at 0 and end at L. And you could start at some other point A and end at B, and then this integral from A to B. But typically, to keep things simple, you would think of one side as being at 0 and the other side as being at the length of the rod. Once again, integrals are not too hard to do. You can do them for your homework. Do them both and make sure you calculate the fraction. And that'll give you the center of mass. What does the center of mass mean? It's the balance point, essentially. You know, if it's denser over here, the center of mass is going to be pulled to the right. Might have to put this is on a teeter-totter. Might have to put the fulcrum over there to make it balance. It's denser over on the right side. Okay, that's the intuition about what it means. It's the balance point. Okay? On Wednesday we will be trying to get into more of explaining these formulas, but let's take our break right now.